Welcome to EPG Pathshala lecture series on computer science. In this module on data analytics, we will be discussing about mining data streams. In the previous module, we discussed about what is a data stream, the general architecture for processing data streams, and then few applications that wherein data streams comes into picture. As the second part of this mining data streams, we will be understanding various algorithms related with mining data streams, understanding and filtering mining data streams, followed by counting elements or distinct elements from streams. We will also know the basics of filtering and counting distinct elements from data streams. So, the overview of this module is as given. First, let us discuss about the algorithms for streams, followed by Bloom filter, which is an important algorithm related with filtering a data stream, and few applications related to filtering data streams. And last, we will be discussing about Flajolt-Martin's approach for counting distinct elements from data streams and few applications related to this particular approach. First, let us discuss about the various algorithms for data streams. To start with, the first kind of algorithm that may be applied on data stream is filtering. Now, what exactly mean by filtering? Filtering is fixing a property and then selecting elements that satisfy this property from the given data stream. So, it is like select elements with property X from a given data stream. And one important algorithm which is related with filtering data stream is Bloom's filter. Filtering data stream finds wide application in terms of data streams. The second type of algorithm that may be applied on data stream is counting distinct elements, because given a set of data stream and elements in that data stream, we may be in a position to identify what are the unique elements from the given data stream and how many number of times those unique elements has occurred and how many unique items are there from the given data stream. So, to do this, we require counting of the distinct elements from the given data stream. One important algorithm that is widely used for counting distinct elements is Flajolt-Martin algorithm. Here, we will be taking say a set of data stream and elements as part of the data stream and then identifying the number of distinct elements from the last k elements of the given data stream. The third type of algorithm which may be applied on data stream is estimating moments. Estimating the standard deviation of the last k elements will help in understanding the distribution of the elements in the given random sample. One important algorithm used for estimating moment is AMS method. So, as part of this lecture, we will be discussing about Bloom filter, Flajolt-Martin algorithm and then AMS method. Counting frequent item set is another important approach which is widely used in data streams. The reason is when few of the items occur together, items here in the sense the elements in the data stream if occur together, then we will be looking in for such frequent item sets or frequent elements from the given data stream. Let us now discuss in detail about filtering data streams. Suppose you have a data stream and assume the data stream has various elements and every element is defined as a tuple. We also have a list of key which is defined by the notation S. Now, from the given S, we will have to identify which tuples of the stream are in S. One simplest solution for this is you can make use of a hash table. So, when you are going to create a hash table, you will have to index the key that is part of the set S. So, whenever a new element comes into picture, you will have to give that element to a hash function which is defined over the key, and in case if the key is part of the given set, then the new element will be accepted or it may be ignored. But the major problem here is when you do not have enough of memory, we will not be in a position to store the entire hash table. In other words, all the keys available in the set S may not be held in the main memory. Therefore, what is that we need to do is, we need to narrow down to a subset of keys that may be of very important for filtering. For example, we might be processing millions of filters on the same stream. So, for every filtering, you will have to make use of a separate hash function. So, when you are working on different hash function, you may be working on separate memory spaces in the main memory. So, therefore, you may not be in a position to accommodate the entire set of keys. What may be an application wherein filtering of data stream comes into picture? One simple example is identifying whether an email is a spam email or not. So, we are trying to filter out emails that are deemed to be spam. We may be having lots of contact email IDs in our inbox, but out of these contacts even some spam may come into picture, or there may be a contact which is not part of our inbox list, may be coming as a spam mail. So, what is that you need to do is, whenever an email comes to your inbox, you will have to identify whether this email is spam or not. If it is spam, then you will have to ignore that particular email, else you will have to accept the email into the inbox. Another important application where filtering of data streams will come into picture is, suppose you collect lots of messages from the web. Assume each and every message that you collect is a news article from the web. There may be many individuals or people who express interest in certain sets of keywords. Now, what is that you can do is, you can take these set of keywords and the messages collected from the web, which are nothing but news articles, and determine whether each message matches with user interest. So, now the user interest can be the key. You can define a hash function based on this key, and whenever new message, that is a news article, comes into picture, you can identify whether that news article is corresponding to a user interest or not based on the defined hash function. One simple solution for filtering is, you should have a set of keys with which you can always define a property, and based on this property you can filter the incoming data element. Now, when you have a set of key, how you are going to represent that in the memory is, you can always define a binary array or a bit array indicated by the notation B, and assume this binary array contains n bits. Initialize all the n bits to 0. Then you will have to define or choose a hash function. You can choose one or more hash functions based on the necessity. Assume you choose one hash function h, and which is going to evaluate in the range of 0 to n. In case when an element S, which is part of your data stream set S, that is the key set S, comes into picture, all that you need to do is, you need to send the element S to the given hash function. If the hash function results in a value 1, then it will be mapped to a specific bucket in your memory. That is, you are going to either consider the input element S if the hash function results in a value 1, else you are going to ignore the incoming element S if the hash function is going to evaluate to 0. Therefore, what is that you can do is, you can take a set of elements from the given stream and consider element by element with respect to the given hash function, and output only those elements that hash to bit that was set to 1. So, if the output of the hash function b of h of a is equal to 1, then that particular element a will be considered, else the element a will be ignored. This solution is diagrammatically represented here in this slide. Assume you have a bit array B having values 0, 1 and so on. As per the algorithm, initially the binary array, all the elements in the binary array will be set to 0. Suppose an element from the set S is taken and if its hash function results in a value 1, then the corresponding element in the binary array will be set to 1. Thereafterwards, when new item comes into picture and if this item is given to the hash function, and suppose if the hash function hashes to a value 0, then you are going to drop that item. Else if the same hash function hashes the element to a value 1, then you will be considering that particular element. So, from the given set S, an element A may be considered or ignored based on the output of the hash function. Now, what is the drawback with respect to this methodology? It actually creates false positives, but it will not create false negative. Now, let us understand what is false positive and false negative. False positive is actually a scenario where a result that indicates a given condition has been fulfilled, but actually that condition may not be fulfilled. What is false negative? It is another test scenario where the result of the test indicates that the condition has failed, but actually the condition may actually be successful. So, what you are trying to do here is something that is wrong is wrongly given as right, that is called as false positive. False negative is something that is right, but wrongly given as false, that is false negative scenarios. So, here in this methodology, when the hash function gives out an output, sometimes it must be given as 1, but your algorithm may result in a value 0. Therefore, that element may be ignored, but this scenario will not occur as per this methodology. So, that is the meaning of it creates false positives, but no false negatives. That is, if the item is in S, we surely give this as an output. If not, we may still output the given element S. Another solution for this is, consider you are working with respect to email addresses. Assume you are having 1 billion email addresses. Suppose if you are going to hold all these 1 billion email addresses, then you may require 1 GB of space for your bit array or binary array, with an assumption that every email address is associated with, say for example, 8 bits. Therefore, totally you require 8 into 1 billion, which is 8 billion bits. So, if an email address is in the set S, then it surely hashes to a bucket that has the big set of 1. So, it always gets through. In other words, no false negatives will be there. Actually speaking, 1/8 of the bits are set to 1, and therefore, 1/8 of the addresses which is not in S get through the output. This is known as false positive. Actually, 1/8 is very less, and less than 1/8 is what is coming into picture when we are trying to address, say, 1 bit from your bucket. So, as mentioned earlier, this methodology will create false positives, but it will not result in false negatives. Let us analyze the false positives in detail. Suppose you want to understand how these false positives comes into picture and how it is avoided. Take a scenario where you are going to throw m dots to n equally likely targets. Now, what is that we are trying to do is, we are trying to identify what is the probability that a target gets at least 1 dot. When you map the given scenario with respect to the algorithm we discussed earlier, the targets will be the bits per bucket and the dots will be the hash values of the item. Here we have m dots and n targets. Now, we are trying to understand what is the probability that a target gets at least 1 dot. So, the overall probability that at least 1 dot hits the target is, say, 1 minus 1 by n. This probability is the probability of some target x not hit by a target. The chance for a dart to hit is 1 by n because there are n targets. So, 1 by n, and the probability for target x not hit by a dart is the overall probability 1 minus the probability of at least one dart to hit the target, that is 1 by n. So, 1 minus 1 by n. This entire probability minus 1 is actually the probability that a target gets at least one dart. Now, here in this scenario, the value indicated within the inner box will equal to 1 by e when this n reaches infinity, and finally put together this entire equation will be equal to 1 minus e to the power of minus m by n, since n is tending to infinity. The fraction of ones in the binary array B will be equal to probability of false positive, which is same as this probability 1 minus e to the power of minus m divided by n when n tends to infinity. For example, you have 10 to the power of 9 darts. Suppose every dart is going to be associated with say 8 bits, then it will be 8 multiplied by 10 to the power of 9 targets. So, the fraction of ones in the binary array will be equal to 1 minus e to the power of minus 1 by 8, which will be equal to 0.117. This, when compared with the previous scenario, is very less when the n value tends to infinity. One algorithm that actually works very effectively with respect to filtering is Bloom's algorithm. The Bloom's filtering algorithm actually takes S values, which is the key values, and binary array which has n number of bits. Here we can choose k number of independent hash functions indicated by h1 till hk. So, here we are going to have just only one single array B. As mentioned earlier, we will have to initialize the binary array to zeros. So, all the bits in the binary array will be initialized to 0. Every element from the set S will be hashed using a hash function hi. So, when you provide the element S to the hash function hi, if it results in a value 1, then you are going to set that particular element into the bucket. In other words, you consider that particular element, else you are going to ignore the element. Now, what may be the time taken for executing this algorithm? Whenever a stream element with a particular key value x arrives, the total time is based on x which is in S. So, based on the independency of the hash function, we can decide the time taken for every element to hash to a specific bucket. Otherwise, we will be discarding it. So, it is all depend on x which is in X. Bloom filter, when it is represented using a bit vector B, we will have to also understand what is the fraction of ones that will be available in the bit vector B. So, when you throw k dot m dots, that is k multiplied by m dots at n targets, the fraction of ones will be equal to 1 minus e to the power of minus k m by n. Since we are having k independent hash functions, we let only the element x to pass through if all k hash elements x to a bucket of value 1. In other words, we will allow x or we will consider x only if all k hash element x to a bucket of value 1, that is all the independent k hash functions must result to a value 1. So, the false positive probability will be equal to 1 minus e to the power of minus k m divided by n, the whole to the power of k, which is dependent on the hash function. Suppose when m is 1 billion and n is 8 billion, then what will be the overall probability? So, if k is equal to 1, the overall value is 0.1175, and if k is equal to 2, the overall probability will be 0.0493. Suppose if you keep on increasing the k, what may happen to k is we will have say the value of k decreasing to some extent, that is a false positive probability will decrease to some extent, and after a point of time you may find it almost reaches to 0, but then it keeps increasing linearly. So, you will be always having an optimal value of k, and this optimal value of k is represented by n divided by m log 2. In this scenario, optimal k will be equal to 8 log n, which is approximately 6. Therefore, the error when the hash function, the number of hash functions that you choose is 6, then the error will be 0.0235. In case if the hash function increases greater than 6, then the error rate will increase. This is what is indicated as part of this graph. So, to summarize, Bloom filter is a very good algorithm for applying filtering over data stream, and it guarantees no false negatives and uses limited memory. This is very good for pre-processing. It actually is suitable for hardware implementation because hash function computations can be parallelized. It is better to have one big B or k and have small b's, but therefore, the probability of false positives may be reduced. So, but keeping one big B is very simple because the number of bits that you are going to make use of will accommodate all possible elements. The second important algorithm or approach that may be applied on data streams is counting distinct elements. Counting distinct element is a problem scenario where assume you have data stream that consists of a universe of elements chosen from a set whose size is n. Now, you will have to maintain a count. The count is going to be a number which indicates the number of distinct elements which has been seen so far from the data stream. One simplest and obvious approach for solving this problem is you will have to maintain a set of elements that has been seen so far and a corresponding count value, and this set of elements that has been seen so far can be accommodated or kept into a hash table based on the distinct elements which is seen so far. What are the various applications that may involve counting distinct elements? Suppose you have many web pages that are crawled by a crawler, say for example a search engine crawler. Now, on a daily basis you want to know how many different words were found among the web pages that were crawled by the crawler in a particular site means, then you are looking in for the number of distinct keywords which is appearing in a given web page. Sometimes the number may be very low or sometimes it may be too high, and in many scenarios whether it is low or high it may indicate even a spam page. But irrespective of this, you can always depend on say counting distinct algorithms for the purpose of defining the number of distinct keywords associated to web pages crawled by various crawlers. The second application where you may use counting distinct elements is, suppose users browse through various product pages in a given online e-transaction environment. Now, if the organization wants to identify how many different web pages does each customer request in a week, then it is nothing but identifying unique web pages that were requested by the users over a period of time, which is once again the problem of counting distinct web pages. Suppose there are many products displayed in a product or a manufacturer's web page, and you want to know how many unique products were sold in a specific time stamp, for example last week. Then you are actually trying to analyze the number of distinct products which has been sold in the previous week. So, these are all few applications that involve counting distinct elements. Now, what may be the problem? The problem when we deal with respect to data stream is storage. Always we have a small storage in the main memory for the purpose of handling the data stream. Suppose if we do not have enough of memory to maintain the set of elements seen so far, then counting distinct elements may result in say a wrong value. In such scenarios, what is that we can do is, we can always estimate the count in an unbiased way, that is you can always limit your elements which is encountered, and you can always fix a probability, a small probability of error which can be added, and with this small probability of error you can always convey the result. So, when we have small storage environment, the probability or chance for error must be considered as part of your result set. One important algorithm which is used for counting distinct elements from a given data stream is Flageolet-Martin approach. In Flageolet-Martin approach, you will have to actually define a hash function h that maps each of the n elements to at least log n to the base 2 number of bits. In other words, you will have to take all the elements which has been seen so far and map them to say a specific binary array. Now, for each element that you encounter, you can define a function r of a which indicates the number of trailing zeros in the hash function output h of a. For example, if h of a results in a value 12 and if 12 is going to be represented in a binary format 1 1 0 0, then r of a will indicate the number of trailing zeros. So, here from the least significant bit you can find there are two zeros, the least significant 0 and the next bit to the least significant bit is also 0. So, it indicates r of a will be equal to 2. Having determined r of a function, next you can define what is the maximum r of a seen, and this may be used for the purpose of estimating the number of distinct elements. So, the maximum number of trailing zeros which is stored in the function r of a will be used for computing the total number of distinct elements, which is mentioned by the equation 2 to the power of r. So, where r is the maximum r of a seen so far. Suppose here in this scenario, if the maximum r of a seen is equal to 2, then the number of distinct elements seen so far will be equal to 2 to the power of 2, which is 4. Now, in summary, we have discussed filtering streams which are widely used for many scenarios. Counting distinct elements for Flageolet-Martin approach is very effective. The effectiveness is because of the hash function that you choose. Here in the given scenario, when the number of trailing zeros increases to a larger number, it indicates the hash value that is given is also large. Therefore, you will have to choose a hash function accordingly, and when there are more number of, that is maximum r which is so large, it indicates maximum number of distinct elements seen. But in reality, considering the entire set of data elements as part of the main memory is very difficult. Therefore, there is always a limitation on the maximum r of a seen so far is going to be limited, but you can always come up with say a variable which can always hold the most recent maximum r of a seen, and you can have a function that keeps verifying whether the recent maximum r of a is less than or greater than the most recently seen r of a. In case if the current r of a is larger, then you can replace the earlier r of a with the current r of a. Thereby, in each and every iteration, you work on different sets of data or different sets of data elements from the given data stream, and accordingly the maximum number of distinct elements from the given data stream can be identified. And therefore, Flageolet-Martin algorithm is very effective for most of the search applications or algorithms. Thank you.